Now, because we did cylindrical and spherical coordinates, it's really, really important to remember how we do change of variables to those, because we don't want to calculate this over and over and over when we do cylindrical and spherical coordinates. The cylindrical change of variables for triple integrals is not too bad. It's pretty straightforward. In this case, it looks a lot like polar coordinates. We take dx, dy, dz, and we replace that with r dr d theta, that's our polar coordinates distortion factor, and then times dz. So we kind of just do stuff in the x and y variable and leave the z variable alone. And to show that that's correct, what we're supposed to do is we're supposed to take these formulas, x is r cos theta, y is r sine theta, and z is equal to z. We're supposed to write down the Jacobian matrix here, which I did earlier because I did not feel like writing it on the slides by hand. And then I'm supposed to take the determinant of that. So the determinant of this, if we expand it out, we're going to get r cos squared theta plus r sine squared theta. And that turns into r. And we get that by going through row by row by row and calculating the determinant in the normal way. And then we're supposed to take absolute value. Absolute value of this is the absolute value of r, but in cylindrical coordinates, we always take our radius to be positive, and so the absolute value of r is still r. That's cylindrical change of variables. Spherical change of variables is a bit more of a cow to actually do the calculation. The point is that we don't ever have to do this calculation anymore once we've done it once. If we figure out what the distortion factor is for spherical coordinates just one time, we can use that calculation forever and never do this Jacobian bit again. Spherical change of coordinates turns out to look like this. It's a little bit more complicated than the cylindrical one. We take dx, dy, dz, and we have to throw in this factor, rho squared sine phi. That accounts for the fact that when our radius is really large, the volume is significantly affected. That's where the factor of rho squared comes from. And sine phi accounts for the fact that areas are very, very distorted near the North Pole and the South Pole there. Something that looks like it might have a big area on a map actually has very, very small area in terms of theta and phi coordinates. And to do this calculation, we take our formulas for spherical coordinates. X is rho cos theta sine phi. Y is rho sine theta sine phi, and Z is rho cos phi. We write down our Jacobian matrix, where the top row is all the partial derivatives of x with respect to rho and theta and phi. Our second row is all the derivatives of y with respect to rho and theta and phi. And our third row is all the derivatives of z with respect to rho and theta and phi. We calculate the determinant of this, and then we take the absolute value. And that calculation ultimately gives us rho squared sine phi. So it's a bunch of trig cancellation, and we can use it every single time whenever we're doing a spherical triple integral. So here's an example. Let's calculate the area, or sorry, let's calculate the volume of the sphere of radius r. So there's a formula for this. The formula is very weird. Most students who see it typically say, why on earth should the volume be 4 over 3 pi r cubed? It doesn't look like it makes sense. It doesn't make it clear where this formula comes from. So let's see how we do this triple integral. To calculate the triple integral, to find volume, we'd usually integrate 1 dx, dy, dz over the sphere of radius 1. But the bounds for that are ugly if we do it in regular coordinates. So what we do is we turn that into a triple integral in spherical coordinates. So we, first of all, take our function 1 that we're integrating, and we substitute in x is rho cos theta sine phi, y is rho sine theta sine phi, and z is rho cos phi into this. But fortunately, that doesn't change the function 1 at all. It just leaves it as 1. We throw in our volume distortion factor, rho squared sine phi, and then d rho, d theta, d phi. And now we have to express our region, the sphere of radius r, in terms of spherical coordinates. The sphere of radius r in spherical coordinates, well, rho is distance from the origin. The sphere of radius r consists of all those points that are between distance 0 and distance r from the origin. Theta, every latitude is allowable, or sorry, every longitude is allowable for doing the whole sphere of radius r, so theta should go between 0 and 2 pi. And similarly, every latitude is allowable, so phi covers its whole range. We should integrate it between 0 and pi. So our first step is we integrate with respect to rho. The integral of rho squared is rho cubed over 3 times sine phi is a constant. And we're supposed to evaluate that between 0 and capital R. And then we got 2 more integrals to do. After that's done, that's fine. And that becomes the integral from 0 to pi, or the integral from 0 to 2 pi of r cubed over 3 times sine phi d theta d phi. Then we integrate it with respect to theta. When we integrate it with respect to theta, this function doesn't depend on theta. It's constant with respect to theta. And so we just get r cubed over 3 sine phi times theta. We're supposed to evaluate that between 0 and 2 pi, like so. That gives us the integral from 0 to pi of r cubed over 3 times sine phi times 2 pi. And then we're supposed to integrate that with respect to phi. And so we have to take an antiderivative. We're basically taking an antiderivative of sine phi at this point. That's an antiderivative of sine phi is minus cos phi. So we get r cubed over 3 times minus cos phi times 2 pi. And we're supposed to evaluate that between 0 and pi. And that turns into a factor. When phi is equal to 0, cos of it is 1. And when phi is equal to pi, we get minus cos of pi is minus -1 is plus 1. So this turns into r cubed over 3 times 2 pi, which is another name for 4/3 pi r cubed if we simplify it. So this is where the formula for the sphere of radius r actually comes from in the first place. If we switch it into spherical coordinates, we get like an r cubed over 3 coming from the integrating rho squared. We get a 2 pi coming from going around the longitude coordinates, and we get a 2 coming from going around the latitude coordinates where we integrated sine. So this is where the formula comes from, and this is where you have to this is where you derive it. There are clever methods for figuring out the radius that are due to like Archimedes, but this is the kind of most straightforward way to do it using multivariate calculus tools.